Dr. Timathy Dellapenna and Justin. Welcome to Kuwait. حياكم الله في مركز علوم البحار. اليوم عندنا الدكتور الزائر البروفيسور تيم ديلابينا من جامعة تكساس A&M University. طبعا كان لي الشرف واني كنت طالب عند الدكتور بروفيسور تيم، كان هو مشرف رسالتي الماجستير والدكتوراه. فولله الحمد والمنه، يعني هي نعم من الله سبحانه وتعالى على عباده انه يعني يتلقى العلم عند دكاتره مميزين في مجال علوم البحار بشتى تفرعاته وتخصصاته. طبعا هو زايرنا هنا مده اسبوع للكويت لمناقشه ابحاث مشتركه بين جامعه الكويت وبين جامعه تكساس A&M University. اليوم راح يعرض بعض النتائج الاوليه اللي حصلنا عليها وبعض النتائج يعني في اماكن اخرى في العالم. Dr. Timathy Dellapenna holds the rank of professor with both the departments of oceanography at Texas A&M University and with the Marine and Coastal Environmental Science Department, also at Texas A&M University at Galveston. He earned his bachelor's degree in geology at Michigan State University, a master in geology, and also a master in hydrogeology, both from Western Michigan University. His PhD is from the Virginia Institute of Marine Science at the College of William and Mary, usually referred to as at VIMS. He is a coastal marine geologist who works both along the inner continental shelf and within estuaries. Although much of his research has focused on Texas and the Gulf of Mexico, he has also conducted extensive research in Prince William Sound in Alaska, Korean estuaries, and has started working in Kuwait Bay. طبعا مثل ما بينت لكم معنا. فنرحب and welcoming Dr. Professor Tim Dellapenna.
Thank you.
It's mobile silent, please. Mobile silent.
All right. Is this working? The microphone?
I think it's working for the recording.
Okay, but I need to talk in this one.
You can,
Okay. Well, thank you very much. I've had a wonderful week so far in Kuwait. I've probably drank more coffee this week than I have in my life. A little bit of tea too, a little bit of shawarma. It's been fantastic. Mohammed has been a wonderful host. We actually got out to Dr. Tarek's farm yesterday up north. It was really great to see the country. And we're experiencing what I hear is a very rare event. I got woken up to a thunderstorm this morning. Yeah, I didn't think that would happen here, but that's great. I'm loving it here. To begin with, I do appreciate this wonderful opportunity to come here. I've been working with Mohammed in Kuwait Bay for a couple of years, and this is the first time I've actually seen it. So that's great. We had a project funded through KFAS, and immediately as it was getting started, everything shut down for COVID. So we had to delay a little bit. I've given this talk a couple times, and I normally talk about Korea, and I forgot to remove my Korean slide right here, so I apologize. That's actually an estuary from Korea. But today we're going to talk about really mercury and how I use it as a tool in estuaries, and also how estuaries have, as a geomorphological system or geological system, respond to human influences. So that's where we see the Kuwaiti system and the Korean system, but we're going to really talk today about Texas. So we're going to start talking, beginning to talk about Galveston Bay in Texas, and much of this work was because of the wonderful dissertation that Dr. Makami was able to did under me. We had a great foundation to look at what happened from Hurricane Harvey, which happened in 2017. And so we'll talk about his dissertation work and how it influenced the work that we were able to do afterwards. And so actually here's some evidence that he did go in the field in Texas. This is working with, I believe, Josh Williams in the summer, in August, during Ramadan. He went out and had a really rough field season, worked very hard, and he actually, this is a photo of Mohammed working in the lab, and often he also had a lab assistant from Kuwait that helped him quite a bit. But yes, he was probably the hardest working student I've ever had. He had 4 years to learn chemistry. He came in to do geochemistry, but I wasn't aware he'd never had a chemistry class before. So he had to teach himself chemistry in English, while also taking his curriculum and doing his dissertation. And in 4 years, he did a master's and a PhD and became a chemist, as well as a marine geologist, which was very impressive. So let's begin with an estuary. Kuwait Bay is an estuary, but it's what we call an inverse estuary. It's the only inverse estuary I've ever worked in where there is more evaporation than there is fresh water coming in. You don't have any river systems here, but in other estuaries I work with, estuaries are where rivers and the ocean meet. And so fresh water flows in from the drainage basin, and salt water flows in from the bottom, and there's a whole lot of dynamics that happen in these systems. And they provide a buffer or a filter between the river water, which is often carrying contaminants and nutrients and organic matter, and they're getting together with the ocean water. And so there's a lot of exchange between these two waters that creates biological activity as well as chemical reactions. So the estuary is the filter. It filters nutrients, contaminants, organic matter. And just like Kuwait Bay, it provides a fisheries, a habitat for fish. Many of our ocean fish are born in estuaries, grow up in estuaries, and then move offshore to other environments. And so they're essential for that. They also, as you all know here, we have shellfish in estuaries. Texas, we have oysters extensively, clams, shrimp. We don't have any lobster. You guys have lobster here. I'm very jealous of that. But we have other crustaceans. And also, as I've noticed here, there's some boats out here in the water. They're recreational areas. And they're also harbors. Almost all the harbors in the world are within estuaries. And what goes along with harbors is dredging, which moves sediment around. The ships come in, they flush their bilge water, they contaminate the system, oil gets spilled. Lots of different things happen just because of the waterways. So they're important to society, and they also are very vulnerable to impacts from society, from humans. And so then they naturally respond to that. Estuaries are threatened by things such as contaminant and nutrient loading from the watershed, from water coming in. And here, it's from outfalls, from water flowing into the bays, from hospitals and from the towns, and from rain today, and from desalination plants and other things that are coming in. Estuaries are threatened by reduction in sediment flows. In many cases, dams get put into the rivers. You don't have rivers here, but we do. And when they put the dams in, the sediment gets trapped behind the dam, and so the dams reduce the flow. So if you don't have sediment in the estuary, then the estuary becomes different. And also land reclamation. You fill in part of the estuary to build out your city, build a harbor. In Korea, they actually filled in the estuary to build an airport. They filled in the estuaries to build cities. Here, we'll show you some examples of land reclamation here. It changes the size of the estuary, so it changes the dynamics. And you don't have that here, but in Korea, they have a lot of estuarine dams. They actually convert part of the estuary into a freshwater lake. We won't talk about that anymore today. So this study, we're going to talk about how changes in accommodation space due to subsidence influences and impacts the estuary, and I'll explain what all that means in a few minutes. And we're also going to talk about how we use historic input of mercury into the system as a tracer to figure out what's going on. Now, mercury is interesting because it's what we call particle reactive. It doesn't dissolve well in water, but if there's suspended sediment, it sticks to the particles and it stays stuck to the particles. And then it moves around, and it's very easy to measure. And it's very quick to measure total mercury. You guys have a mercury analyzer. We have one. In fact, I had just been given one by someone who had moved away. And I thought, I have a guy who wants to do geochemistry. Why don't I have him use this mercury analyzer? And so that's kind of how we started using it. He was the pioneer in my lab and what we could do with mercury. And we've done a lot with it since. So, okay, let's talk about an estuary versus a delta. You have a delta right around the corner, a little north of you and a little east, on the Tigris-Euphrates. And then you have Kuwait Bay. In Texas, we have the Brazos River, which is a major river. It's the 11th largest river in the United States, and one of only 2 deltas on the Gulf of Mexico or the Atlantic, the other one being the Mississippi. And they both are very similar. They have rivers, in this case, the Trinity River in the San Jacinto and Buffalo Bayou flowing in. This is Galveston Bay. I apologize, I don't have a bigger map. I didn't think about the fact that you may not know where this is. This is the Gulf of Mexico, the southern part of the United States. And this is Galveston Bay. This is the Brazos River. When sea level was lower than it is today, it was, 130 meters lower 20,000 years ago. Both of these systems were valleys with rivers flowing through them. As sea level rose, the valleys became flooded with water. Galveston Bay is still flooded with water. The Trinity River isn't. I mean, the Brazos River is not. The difference is this had so much sediment coming in it filled the valley. Sediment isn't so much in this system, and so the valley hasn't filled. It's remained as an estuary. And so for an estuary to exist over the 13,000 years of the Holocene, then what you need to have is a situation where sedimentation is about the same as sea level rise. If sedimentation is higher, it fills and becomes a delta. If it's lower, then it still stays oftentimes part of the continental shelf. So you have to have this balance. And so geologists use this concept called accommodation space. If sea level rises, then there's more space to fill sediment. Or if the land sinks, then you create more space and it fills with sediment. And so for the system to be remained as an estuary, there's a balance between erosion and sedimentation. But if that balance is interrupted because sea level rises, then the sedimentation is going to increase. Or if the land sinks, then the sedimentation is going to increase. And so in Galveston Bay, we're just going to jump to this right here, the land sank dramatically from 1906 until 2000. In some areas, it sank as much as 3 meters. The land sank, so we created accommodation space. And it sank because we pumped so much groundwater to support the refineries and support the city of Houston growing that the clays in the aquifer collapsed and the land sank. And you can't rebuild those clays underground, so the land stays sunk. So I had just started considering this when I had dropped in my lap a Kuwaiti student who wanted to do a dissertation, and he wanted to work locally. And I just had a friend who said to me, hey, has sedimentation kept pace with subsidence? Did the sediment in these areas where the land sank, did it increase? And so we decided that would be the focus of his dissertation. And so he went out and he tested that question. And so this is just a little more on Galveston or Houston. Houston is the 4th largest city in the United States, and it's a new city, kind of like here. The population has dramatically increased in the last 100 years. So the red line here is population growth, and the green is groundwater use. And as you see, I'm just going to move this around a little bit. There's a dramatic increase. So they started pumping groundwater, and the land started sinking. And then they shifted away from groundwater and started using surface water from the rivers. And so they've cut that off, but the ground sank, and it's continuing to sink as a result of that. And so this is looking at a map that Muhammad made, Muhammad made this map using GIS because he took GIS classes as well. And this is looking at the contours of subsidence and the contours of sedimentation. Now, there's a deep valley that was carved out in the bay from when the sea level was lower, and that's what the gray is showing. But what we see is that the areas where the sedimentation rates are the highest are also areas where the subsidence is the greatest. And so if you think about this idea that sedimentation keeps pace with the formation of accommodation space, sea level is rising at a rate of globally about 2 millimeters per year. And we get to the distant parts of the bay here and over here, the sedimentation rates are about 2 millimeters per year. So the sediment is accumulating at the same rate that accommodation space is being formed from sea level rise. And you see that throughout the world with estuaries. If the sedimentation rate is higher than that, then something's going on. The system's been modified. In Korea, it's because they put dams in it. Here, it's because we have subsidence. As it turns out, sedimentation has not kept pace with subsidence. Sedimentation rate, the subsidence rate is about 3 centimeters per year, but the sedimentation rate is only 2 centimeters per year. And that's because they actually have dams in the system, and there just isn't enough sediment coming in to keep pace. So some areas have gotten deeper, but it's still an order of magnitude, a factor of 10 higher in the areas where the subsidence is higher. That's what we found. And oh yeah, here's a paper written by Mohammed Al-Mukami. This is a second publication, I think. And we published the results of this. And so this is, we go to Upper Galveston Bay. And that's what, if you can see the cursor at this area up here. And this is where the Port of Houston is. So we have the Port of Houston, the tankers have to come all the way up the bay, and then the refineries are mostly up there. And so Galveston Bay is on the average about 2 meters deep, but then there's a ship channel that's almost 20 meters deep that accommodates the tankers. And it's the busiest shipping port in North or South America. And it's the second highest concentration of refineries in the world. And so this is looking in the upper portion of Galveston Bay. And so this is the area we call the Port of Houston. And this is actually a system called Buffalo Bayou. We'll talk about that in a little more. That's where most of the refineries are. And it's also a river that cuts through Houston. And there's one site right here where almost all the mercury has come into the bay. So this is showing most of the refineries and chemical plants around the bay. And this is one site called Oxyvinyl. And this is just showing you Patrick Bayou, the little lightning bolt right here is just showing where that is, where we're focusing up here. And so we'll talk about that in just in a second. So all the mercury is coming from this one site over here that we didn't go to for Mohammed's dissertation, but I've been to afterwards. And most of the mercury is concentrated up here because it's right near the site where the mercury is coming in. And we published another paper that looked at the mercury within Galveston Bay. And this is looking at the concentration of mercury in the bay in 2013. What's notable about this is in 2017, there was a huge hurricane, and the hurricane came on land and brought massive amounts of rain that caused this map to give us great baseline data because everything changed after that. But I had the advantage of having this work that Mohammed did in my back pocket. When the storm came, I was able to have a baseline data to see, okay, how has things changed? And that's what we were able to do with this study. And so we have concentrations in general within the bay ranging from 6 micrograms per kilogram or nanogram per gram. Parts per million is another way of thinking about this. And then we had some areas as high as 162, which is pretty high. Within this area up here, we call the San Jacinto Estuary, the area in the box up here. The average was about 150 nanograms per gram of mercury. In other parts, 20 to 50, as low as 8. So this is where the mercury is coming from. It's one plant that's discharging it into the bay called Patrick Bayou. And it's just a zoom in. I'm going to zoom out a little bit. This is where the plant is. There's a little bridge right here. You can't get a boat under the bridge. So in Texas, if you can get there by water, then you're allowed to be there. Except I had to get permission to come up here because it's a secure area, but still, the company can't keep me from going there if I can get there by water. Now, I can't get under this bridge because it's only about this high off the water, but I was able to get in right here and get some cores. And so this is just giving you an idea of where that plant is. This is Buffalo Bayou. This is all the refineries in ports in Houston, and then this is going down to Galveston Bay. A little further out, Buffalo Bayou, Patrick Bayou up here, our site, and then this is all of Galveston Bay. Our university is down here. I live over here. So I got up in there. So this is that little bridge. This is Patrick Bayou, and we took a core, and this is the core. And so what this is this was collected after the hurricane, and this is showing this amount of the sediment that was deposited after the hurricane, and actually this was eroded and then sediment was deposited on top of it. And this is looking at the concentration of mercury. As I said, the bay is on average about 20 to 50 nanograms per gram. This core was 51,270. This is higher than any mercury that's been reported for Kuwait Bay, for instance. Really, but it's right next to the site within a kilometer of where it was discharged. Really high. This is some of the highest mercury concentrations found in sediment in any estuary in the world. And so that's the source. And even above that, in the storm deposit, it's 3,000. So yeah, I wish we'd gotten there for you. So we looked at the impact of Hurricane Harvey on a redistribution of mercury, and you'll see there's a name familiar right here as co-author. We used this data. And so we'll just talk about this study a little bit. So Hurricane Harvey came in, and this is looking at the drainage basin for Galveston Bay and the rain. It brought in 11.1 billion cubic meters of rain. Yeah, that's a lot of rain. Or 3.6 times the entire volume of the bay flowed through the bay as a result of this, with much of the water flowing through the bay in 7 days. But for various reasons, the flood lasted 44 days in parts of the bay. So this is just looking at different rivers in the discharge, the hydrograph for the river. So this is the Trinity, this is Buffalo, another Trinity River, and then this is Buffalo Bayou, and it lasted much longer. And I'll talk about that in just a second. But this is the Galveston Bay drainage basin, and this is the most intense rain. So it all came in here. And so this is the western side of Houston, and there's a place where they measure the water here, they measure the river flow here, and so this is for instance the San Jacinto, and what this shows is there was a 7-day flood here. But these features right here are areas where they built big areas to retain flood water. They have dams in there, and they were built in the late 1940s. And in Texas, we don't have rules so much about where you can build things. And so people actually built neighborhoods inside of this reservoir because it's usually dry. And then it flooded. And neighborhoods started flooding. And so the Army Corps of Engineers, which is the organization that manages the water, opened up the dams, and then they flooded the river down below the dam. And those people all got flooded. And they slowly released the water for about 50 days. So they prolonged the flood for 50 days. And as a result of that, there was a lot of erosion. And so this river flows all the way across Houston, through the refineries, and it flooded for 44 days. I have 50 days here, somewhere in there, 44, 50 days, somewhere in there. And it caused a lot of transport of contaminants within the bay. And these black dots right here represent all the oyster reefs in Galveston Bay, oyster beds. So we'll just go past this. I already talked about it. This is a simulation of freshwater flow during the hurricane. Galveston Bay is never fresh, but it was fresh for a week. 7 days it was fresh. It killed off the oysters, actually. Now the floodwater is starting to retreat, and we're going to see Yeah. Yeah, it's retreating up into the bay now. I'm sorry, that's the simulation again, but you get an idea that it was pretty intense. And so what happened was the first part of the flood, so much water came through, it just flushed out and eroded the sediment here, flushed it out, and flushed it straight out of the bay. But because we did the slow release of fresh water from the bayous over here, fresh water got trapped in the bay for 100 days and just circulated around the bay and moved the sediment and contaminants around the bay. It also killed off all the oysters in the bay for a year. They're back. I love oysters. They're good to eat. And it trapped a lot of sediment and contaminants up here. So that's what these arrows are showing, is that it trapped stuff up in here. And so we went out the storm happened at the end of August, and we went out in October, because I was off on other research cruises also looking at other aspects of the storm. And this is the mighty Lithos. When Muhammad was with us, we called it the Big Daddy. It's the boat that we used to core, my mighty research vessel. And much to the chagrin of Muhammad, I have women driving the boat and women driving the truck. But yes, sometimes it's all women out doing the field work for me. It's great. And we went around the bay, and we actually pushed this thing into the water. It lets water flow out of it. You pull it up, the sediment gets trapped in it. And we went around the bay, and this is actually looking at this is the flood layer right here. You can see the flood layer in brown here, and then the pre-flood layer here. We took some longer vibrocores. That's Lindsay right there. She was a graduate student that worked with us. And went all over the bay. So here's some results. This is actually a core from Muhammad's dissertation. This is a bay called Scott Bay. It's an area that's heavily impacted by subsidence and by mercury. And this is just looking at the mercury profile. This is actually from Muhammad's dissertation. And we're seeing really high, almost over 2,000 nanograms per gram of mercury in this core. And we thought, wow, that's really high. Until we took that Patrick Bayou core, was 54,000. But this was a really high profile. And then we were able to match it up. We went after the storm, we collected another core. And we were actually able to match up the peaks. And then this is looking at an X-ray of the core. So we have a veterinary unit that allows us to shoot X-rays so we can see the internal structure of the core. And what we see is that this red line right here is the flood layer. And it eroded the core down. And because we can compare these two, it eroded the core down 48 centimeters. So we removed 48 centimeters of sediment. And then we deposited 22 new centimeters of new deposit. So we eroded a half a meter from this area that contained heavily contaminated mercury sediment. It got transported into the bay. And then as the flood retreated, we deposited a new layer on top. And that's what this is showing. And so I'm just going to go through that. So we eroded, and then we deposited a new layer on top. And we went around the bay, and we measured how much, because we were able to look at how thick the flood layer was, we were able to measure how much sediment was deposited in the bay, and also how much mercury was in that sediment. So the flood deposited, and these are numbers that are a little old, about 149 million tons of sediment into the bay, which is equivalent to about 25 years of sediment discharge. So 25 years of rivers flowing in the bay is equivalent to one Hurricane Harvey. And if you look at it on average, it deposited about 14 centimeters of mud across the entire bay. And that sediment contained about 5 tons of mercury. And since then, we've actually gone back out, and I'm not going to show that here, and in the last 5 years, about 20% of that has been eroded away. But it's still there. And it's deposited all the way across the bay. And so we were able to make these assessments because we had the pre-Hurricane Harvey map that Muhammad made, and we did post-map, and we were actually looking at how things changed in the bay. And so we had a huge amount of sediment coming in, and we also delivered a lot of mercury to the bay. And we're able to do it. So what happened was that because the land is sinking, the sediment is accumulating, it's containing contaminants, and those contaminants are elevated, and because the sedimentation rate is so high, we create this big storage of contaminated sediment. And the thought previously was, okay, no big deal, it's just trapped there. Well, guess what? When you get a hurricane, it all gets flushed, and it's like a time bomb waiting to get reintroduced into the environment. And that's the take-home message from Hurricane Harvey in Galveston Bay. So let's talk a little bit about Kuwait Bay. So I said Muhammad's group, not me, went out and have collected a whole bunch of cores around Kuwait Bay. And we're going to focus, this is all the cores we've been collecting, but we're going to focus in the Hishan area down here, and we're starting to focus in this area as well, but I'm not going to show any results from over here. It was at the Jahar area. Again, we have Muhammad from Texas. Just had to show that again. You know, at least he didn't fall off the boat this time. And we know Kuwait Bay, so I'm not going to spend, this was a talk one of my students put together for his group. We know the system. One thing that's interesting here is that, oh, come on. Well, we'll go back to what's interesting in just a minute. So anthropogenic alterations here, we have dredging going on, and dredging moving sediment around. And we have outfalls, which we'll talk about in just a minute. They're eroding sediment. But what are the sources of sediment for Kuwait Bay? Where's the sediment coming from? I'll ask you all. It's your bay. Where does the sediment come from that we find in Kuwait Bay? Any ideas?
Start with the students.
Yeah.
Our students, lovely students.
Anyone? Yeah.
Iraq and sewage.
Iraq. The Tigris and Euphrates River. Yeah. Sewage, some, but there's another source. Pardon? Yeah. Dust. Yes. Dust storms. And there's another source you probably don't think about. It forms in place. It doesn't, well, it does form in place for us. What kind of sediment do you have in Kuwait Bay? You have dust-borne sediment, but you also have sediment forming in place through the precipitation of calcium carbonate. This is an evaporitic system. Evaporation rates are really high. As a result, calcium carbonate concentrations are really high. And when the shamal blows, it creates the sediment, the dust settles, and then it creates opportunities for calcium carbonate to precipitate out of the water. So your system is largely what we call a calcium carbonate system. So you also have sediment produced within the bay. But on average, the sedimentation rate in the bay is about 1 millimeter per year. It's really low. In fact, it probably isn't keeping pace with sea level rise, especially since Iraq isn't sending you as much sediment as it used to, right? Nowhere near as much sediment. So you're kind of on the edge of the delta, but they turned off the spigot up there. And so you don't have much sediment coming in. And it has impacts to the environment. But we're going to show you that parts of Kuwait Bay still have pretty high sedimentation rates. So I'm not going to go through that. You guys know more than I do what direction the wind blows and how hard it blows. So I won't need to tell you about that. You also know how dry it is, usually. Not today, though. But you know the wind comes from Iraq and from the northeast in different directions, different times of the year, and that's a source of sediment. And also it's an inverse estuary. You have water coming in from the bottom, from the top, evaporation, the water gets dense and it flows out of the bottom, which is the opposite of what we have in our estuaries. And because of that, you have carbonate-enriched water sinking, it gets cold, and calcium carbonate precipitates when it gets colder rather than warmer, and so you have more, actually it dissolves more. Anyway, you have more opportunities to precipitate calcium carbonate. So this is just the inverse estuary. If water flows in, Evaporation, the water gets dense and it flows back out of the bottom because you don't have generally much river input. We also have areas where we have high mercury input. This port system right here, there was a desalination plant, and that's the major source of mercury for Kuwait Bay. And it's a pretty significant source in the past. From the 1960s through the 1980s, they dumped mercury into the bay as a waste product from the desalination. And that's pretty common in Texas. We had polyvinyl chloride plant doing the same thing. It was just dumps it into the bay. And the same thing in the United States. We had no laws that protected us from having that happen until the 1970s. And so this is an older map. And I want to point out, most of all of the research that's been done in Kuwait Bay has been done by chemists, not geologists. And they're either looking at radioisotopes from fallout from Chernobyl, or they're looking at surface sediments. So they didn't take cores. No one's taken cores. They've only taken surface samples. And if you take the core, then you figure out what the whole story is. If you take the surface sample, you don't. And so that's why it's kind of relevant what we're doing. So this is where they found mercury. So this is a great image. I love this image. This is from 2017, and it's a low tide image from Google Earth. It actually allows us to, I'm not going to pronounce this. I'll butcher it. I don't want to hurt your ears. I'll just call it Heishan. Area, low tide. And what do you see here? You see the Jahar outfall from the desalination plant over here. This caused tremendous erosion. We're estimating this is about 3 meters deep. I actually did the estimation a few minutes ago. If you take the volume of sediment that was eroded from this outfall and you spread it across the low tide area right here, you have over 1/2 meter of sediment that could be deposited in these areas. So it's pretty significant. So you have a system where sedimentation rates are at naturally about 1 millimeter per year, but then you have these outfalls causing tremendous erosion. Here, all the green dots are outfalls. The red dots are our cores. We don't have great core coverage, but we do have core coverage. So when you look at the literature, as I said, none of the cores were deep enough to really see what's going on in the system, previous work. And they didn't have x-rays, and they really weren't doing geology in the previous work. So that's one of the things that we've been able to do. And they didn't have broad coverage. So we're just going to talk a little bit more here. So we divided the bay into the upper bay, the mid bay, the west bay, and the lower bay based on what we're seeing in our cores, and they're clearly different environments. This area is heavily influenced by the sedimentation from the outfall. This area is influenced by the building of the bridge and sedimentation as a result of the building of the bridge. This area is dominated by these outfalls in the southern bay, and these areas are a little different. They're getting sediment from various sources. So upper bay area where the bridge landing is, you have Tuttle Inlet here, you have a lot of construction, and it actually caused high rates of sedimentation of sand in this area. This is an interesting story. There's an outfall here, and about 10 years ago, they created this spot right here by creating new land. We call that, there's a dredge spoil placement area. It appears that they're dredging the harbor over here that contains a lot of mercury, and they're dumping it right here. And then it got opened up, and the mercury-laden sediment is making it out here into the bay now. Southern shoreline, you have these outfalls, places where they have a pipe and it discharges water from town, from sewers, from hospital, from various sources. And as you can see, they all create little channels that cause erosion, and the sediment gets moved back into the bay. So this is the major outfalls, places where the water is getting discharged into the bay, with this being the largest and most significant over this one up here. And this is the Ryan Reclamation area. You can see 2004, there was nothing here. August of 2004, they started building it. 2008, it's built, it's filled. It's not opened, and then in 2012, it breached and it started discharging water into the bay. Here we see the land reclamation. They're filling in the land to build the port over here and the bridge landings. And so this is an area where they've expanded the land and filled in the bay. And when you do that, you also end up adding sediment to the bay. So this is one of our cores. This is from up here where the bridge landing is. And you'll see the yellow is sand, orange is silt, the black or the gray is clay. And this is looking at mercury concentration. And then this is looking at radioisotopes, lead-210. And so what we see is that down here, mercury was pretty consistently low. And then it started changing. And the sediment distribution started changing here. That's when they started building the bridge. And so we had a different kind of sediment getting rapidly accumulating. It went from slow accumulation to rapid accumulation as they built the bridge. And a little, not a lot of mercury, but a little more mercury here. They're really not that contaminated in this area, but higher deposition. This core is accumulating mud. It's on the low tidal flat. This core I'm not showing is accumulating sand. It's high on the tidal flat. Okay, yeah, this is D1. This is high on the tidal flat, and it's accumulating sand. And you can still also see that disturbance layer as a result of the sediment changing and also the mercury content changing. So you can actually go in and see when we started seeing the impact of modifications on the bay and what that interval of sediment is. So we had really slow sedimentation, and then we started modifying it, and the sedimentation rates went up dramatically as a result of that. HC1, all the way down here, is the one place where we have really high mercury contamination. Mercury over 300 in this area, which is the highest we see in the bay. And we also see a big transition down here and really high sedimentation rates. This is a sedimentation rate of 1.4 centimeters per year, which is over 10 times what the natural rate would be. So we're accumulating mercury at the very surface, but we're also accumulating sediment. So this is 2012 when that retention pond breached and we started dumping mercury into the bay. And we can just see that right here in the mercury concentration. We can actually use we know the history of the bay. We know when the mercury was introduced, so now we can use that as a geochronology tool. And here's another core where mercury isn't quite so high, but we also have almost 1.47 centimeters per year, so really high sedimentation rates. And that's because of, this is actually out in the bay, and that's because we have the erosion of the sediment ending up in the bay. So it's, the outfalls are eroding sediment that's getting distributed across a system that normally has really low sedimentation rates. And we can look at the concentration of mercury here. You can actually see that previously, before the bay was disturbed, the sediment contained almost no mercury, like below 10. Previous workers had said it was 30 nanograms per gram, but they weren't taking cores that went deep enough to get to older times before humans started altering the system. So they were already looking at altered sediment because they weren't looking at cores, able to get back to where the mercury was highest. So we made a map that looked at the sedimentation rates, red being high, blue being low. We see the highest sedimentation rates right up here with the, right by where they built the bridge on the beach, and fairly high sedimentation rates all across this portion of the bay. But we only have a few cores. We have cores here, we have core here, we have core here. We don't really know what's going on here, so we're just estimating what's going on here. When we run the seismic in a few weeks, we'll have a better idea of what's going on up here. Low sedimentation down here. However, when we look at mercury, one place. We got this area where they put the dredge spoils. It breached. We have one core over here, and that's where we see all the mercury in this portion of the system. So plug up these holes right here to cut off your source of mercury to the bay. We came up with something that no one knew about And we also have a solution. That's pretty simple. The mercury that's there, it's high. It isn't going to kill you. You don't want to have it there. So you can solve the problem pretty easily. So we actually came up with pretty interesting results. So again, this breach right here is probably the source of the mercury. If we came up here and got some samples in here, and we had high mercury concentrations, then we'd be able to confirm it. And that's kind of an interesting story. So from here, we have a setting where, I just lost my screen, but I have yours. It was dredged here, it was dumped here, and it's flowing into the bay. Here, that's the mercury dispersal. The sediment dispersal is largely, dominantly from either coming through up here or coming from this, and then getting moved into the bay and getting deposited in the lower energy portions of the bay. I say lower energy. This system's macro tidal. You have what's your tidal range here?
Tidal range.
2 meter tide, 2 to a little over 2. Tidal range where I work, 25 centimeters. So yeah, a little different for me. Korea, 30 meters in some cases, not 30 meters, 10 meters, 10 meters. Here, so when the tide is high, the water gets up here. Otherwise, when the tide's down, this is a lower energy setting and higher. This is where you have the area where it is always underwater, sediments accumulating. So that's my conclusion on the Kuwaiti story. Next, we're going to start focusing on Jahar area, but we really don't have any results from this yet. So that's where we're going next. And so what we found, if we can contrast these two systems, is both systems are contaminated with mercury. We can use mercury as a tracer to look at the other things that are going on within the system. And let's see. In the case of Galveston Bay, it was a storm that redistributed the sediment and the mercury. Here, you got two things going on. You have sediment getting redistributed because of the erosion from the outfalls, and you have mercury getting added to the sediment, mostly from the placement of contaminated dredge spoils that are leaking into the bay. So that's what I have to say. Thank you very much.
Thank you, Professor Dellapenna, for the talk and questions, please.
Yes.
Yes.
Thank you very much.
Oh, you're welcome.
Yesterday, Mr. Isa Ramadan, who is a specialist in weather forecast, told us that in these years, the seasons are shifting backward 2 weeks faster than before. So during to the climate changes, do you think that will affect on the sediment height, to the concentration of the mercury, or the direction of the sediments during to the shifting of the seasons?
Well, I think what might happen is with the shiftings of the season, you're going to shift and either increase or decrease the amount of rainfall, right? Yeah. And I think that's going to be the major effect is the rainfall creates erosion and brings sediment into the system. If you reduce that, you may not get as much sediment, but then it'll also change the circulation of the bay. I think those are the major sources. So, however, if you have a decrease in water, of rain, you're going to increase desalinization, you're going to increase discharge of water, and that's going to increase the erosion. And I see that's where the relationship really is.
So the shape of the shoreline will be changed?
Well, the shape of the shoreline will be changed because sea level is rising. But the change of the shoreline where you have these discharge points will definitely change. Yeah.
Thank you.
You're welcome.
Yusuf, please.
Regarding the concentrated mercury you found on the, what was it called before, was HC1? HC1, I think.
Yeah, next to
Yeah.
The reason was that they dumped, when they were working on it, they took stuff from the east and dumped it inside here.
Yes.
That's what we're guessing, yes.
That's, yeah.
And then it leaked out.
So first, one question is that the correct practice? Second, how would they dispose of this waste?
Well, that is,
Concentrated there, as you
is that the proper way of doing it?
yeah.
That's an open-ended question, because proper from the standpoint of, is it environmentally safe, or is it proper because it's legal? I don't know. But from an environmental standpoint, it's been done.
Yeah.
What needs to be done to protect the environment is to contain it and not allow it to get into the bay. Is there a better place to put it? Well, if you put it on land, then you don't have much groundwater. So it's probably, if you put it on land in Texas, that would be a problem because it would flow into the groundwater. But here you probably aren't using groundwater so much, so that may not be a problem. You could dump it in the Gulf, and there's a saying we have, the solution to pollution is dilution. Not saying that's a good solution either, because you're still putting mercury in the environment. It's a tough thing, it's a tough question. The best thing to do is, if you're going to put it in a place, make sure that it doesn't leak.
One last, where did it come from? Since they took it from one place and put it in
Where did the mercury come from? Mercury came from the outfall, the desalinization plant that was up there in the 1960s that dumped sediment into the bay. Yeah.
Chloralkaline.
Yeah, from this right here.
From here.
Yeah.
From here, there's a chloralkaline plant, and they use mercury salts to produce chlorine.
Mm-hmm.
And they used to dump it, and they shut it down in 1986. The chloralkaline, however, there's still legacy contamination of mercury within the system.
I think it was like 30 tons of mercury that got dumped into the bay or something.
Yeah, and the residence time of mercury, we're talking about thousands of years.
Yeah, it doesn't break, it's an element. It's not like it's radioactively decaying into something else. It's still always going to be there.
Yes.
Solution to pollution is dilution. And you don't have much dilution coming in because you don't have much sediment coming in. So it's there.
So when they do the dredging, they reintroduce the mercury again to the water column.
Yeah.
And so you move it from a redox environment to a more oxidized environment that's going to take its journey towards fish, you name it.
Well, that's another point we hadn't made, was we're only measuring total mercury, but mercury is toxic in the methylated state. And the sediment, once you get buried, the sediment becomes anoxic, and the anoxic environment allows it to methylate. So it's the most toxic form of mercury that's being dredged up, unfortunately. So we have problems where we are, and when we dump it, we have it in places where it's contained and it isn't allowed, presumably, to get into the environment. And so that's the reason for having a Marine Science Institute, to educate folks and saying, okay, and this is an easy fix. This is a really easy fix. Some things aren't easy fixes. Easy things to remedy.
Yes.
Yeah.
Question, Dr. Fatma, please.
Thank you for the great talk.
Oh, thank you.
I'm just so shocked for the results. I'm also so curious about, should we do the studies, like further studies on every outlet that coming out of Kuwait?
That's one solution. Some probably aren't. It depends on what they're delivering. We looked at mercury. You could look at something else. You could look at pharmaceuticals. That's a big one. Wastewater pharmaceuticals don't break down necessarily, and they get into the environment, and they do endocrine interruption and other things. So we just looked at mercury. You could look at pesticides,
pesticides,
Pest- yeah, PAHs, yeah.
From what I know, the Al-Ghazali outfall, Majroor Al-Ghazali, is the worst and the most contaminant thing that coming from Kuwait, where since an industrial area, we have a lot of cars, car shops, even the hospitals, I believe.
Yes.
Everything gets dumped in that outlet. So
We have the cores, they're easy to collect. Other things could be looked at. And when we did Mercury, and then we also followed that up looking at polyaromatic hydrocarbons, PAHs. We found a dramatically different story, and also another impressive story, but the sources are different than the one source for Mercury. And so that's the nice thing. We're now the important thing in trying to do these studies, though, is having a geochronology of your cores, understanding what the history of the cores is. And if you understand, and that's what we do, and then you can say, okay, well, let's look at these other contaminants in the cores. And we already have the geochronology worked out, so you can also look at other impacts. I think that's really great. I think that I'm excited for you guys that we're actually moving in this direction.
We're going to build up to it. And
Yeah.
The other thing, doing geochemical studies is expensive. It's very expensive. So,
Yeah.
If you want to do all the spectrum of contaminants, we need millions of dollars for sure. Other questions, please? Faris, please?
If the dams upstream,
Mhm.
Tigris and Euphrates
Yeah.
River, if they were opened,
Mhm.
there was more input from the freshwater sources, would it dilute the mercury, or would there be more input of mercury coming upstream?
Well, that's a good question, because you're going to release whatever's contained in those sediments, and who knows what's in those sediments. And so that's also going to get introduced into the system, and a portion of that will get over here. And so that's what we say a double-edged sword. Yes, you're increasing the freshwater input, you're increasing the sediment input, but we don't know what you're getting. And so that's a good question. The other question is, are they going to do that? That's out of your control, hopefully.
Most of the dams in Turkey and Syria, further north.
Well, yeah.
Not just in Iraq, the dams, it's further north.
That's a big problem with, like, Vietnam has the major river, the Mekong Delta. It doesn't flow anymore because China dammed it up, and they're not getting the water. But if that dam broke, all of a sudden there'd be a big problem downstream. So that's one of the things we're finding in places is that just because there's a dam there doesn't mean that dam stays there. And when the dam, other things, when there's floods, that stuff gets flushed into the system. But, that's a good question, and I don't know. Yeah.
Take the last question. Last two. So, no, please.
You were talking about the cores as, it gives you a chronological history
Mhm.
of what was happening in the environment. I only know about cores through Jacinto River, but I'm curious for both of you to answer. Are there ways to read a core that would determine, whether there were extreme weather events? Because you mentioned
Yeah.
Hurricane Harvey showed up
Yeah.
where the flood line was on your core. So how far back in time can you go and look at weather events without the context of knowing there had been a weather event?
I have a colleague who works in the Bahamas, and he's gone back 50,000 years. And so it's just a matter, we use different tools. We use carbon-14 when we go back further in time. And in these systems, what you'll find is that when there's a flood, you'll probably see more sand in the sediment out in the open bay. And so, yeah, you can definitely do that. You can go back and you can look at a whole lot. There's a whole science of doing that, absolutely. That's not the science I do, but there's other people who do that. Yes, absolutely.
I'll add to it using XRF, one of the tools. So
Yeah.
Each storm has its fingerprint. So using a specific tool like XRF and other chemicals, so you can trace, this is for sure from storm, because you have the fingerprint of the storm. You use the relative ratios of some elements, and from these ratios you can tell whether it's high or low. So if there's high iron, there's more sandstone, for example, less iron, so something like this.
So it's like key identifiers.
Yes.
Something like this.
Absolutely.
And, going back in time depends on the isotopic tool you're using, whether carbon-14 to take you roughly 20,000 years, 20,000 years, yeah, back in time. Other isotopes, maybe potassium, uranium, further, million of years.
Yeah.
But usually we don't go that
That,
far.
I don't do that, but other people do. They go back.
Also, they do it in ice core. They go back in time and they reconstruct the atmospheric CO2 and oxygen in the atmosphere.
Well, Texas A&M hosts the International Ocean Drilling Program, and they're going out with a drilling ship around the world and getting long cores that go way back. We're talking tens of millions of years in some cases, and looking at the details. I don't do that, but that's just, so yes, it can be done across all kinds of time scales. Here, it would make because this bay didn't exist 20,000 years ago because sea level was lower, your bay is very, very shallow. It actually didn't exist probably 10,000 years ago. So we have a short history, and the sediment probably isn't that thick. So definitely it could be done with the technology you have today. We just started.
We're using cesium, lead-210, plutonium, beryllium-7, just to take us a few years ago.
Yeah.
I think who was that question? Yes, okay. Huda?
Up here, we had a question up here.
Yes, thank you. That was good, the answer from all the students. But today I would say really appreciate that.
Oh, thank you.
Because even the Dr. Mohammed Jamie, they took us back to since how many years? I don't say how many years. My minor was geology in Kuwait University. But it is good, there is good problem. When I see that before the slides, they gave three kind of colors for the clay. So from the gray up to the yellow one.
Yeah.
It's bad. But the question is, what the solution? What the solution for this is? Yes.
Sure, if you're referring to this slide.
Well, he's looking at this. I want to say it's really exciting. You guys have the opportunity. You didn't have a marine science department until a few years ago. You didn't have a marine science center. And nothing has been done here, which is great because you don't have to, I want to do that, but someone else already did it. It's a wide open field. You guys can have major contributions that years from now, you'll be the one who did it and someone else will be citing you because you are the major source of knowledge on this system. I lived in Virginia at an institute where they'd been doing research in the same place for 50 years. And I didn't have that opportunity. In Texas, I do, because I'm the only person who does this kind of work. But here, again, we're coming to a place where no one's done anything in the context of what we do. And so it's exciting. You guys have all these, we're laying the groundwork for what you guys will be looking at in the future. Okay, so this is looking at the sediment, the grain size, sand, silt, clay. What was the question?
Was that the different colors of the varieties of colors? Gray start from the gray, after the yellow color is it? The gray color.
The color reflects the grain size.
Yeah.
So this is clay, silt, sand.
Oh, okay.
So this is the,
Yeah. We have an instrument that measures the size distributions very quickly. So it's something that we do. Yeah.
And just to add to it, there's no chemical differences between them, just grain size differences.
Yeah.
Yeah. So thank you, Professor Dellapenna, for this wonderful talk, and thank you for honoring us and visiting Kuwait for the first time, Justin for the first time as well. I hope it's a great experience to you. Yesterday they had the very fresh camel milk. Yes, and
30 seconds.
Yeah, and they have it for breakfast, I guess.
Mm-hmm.
Yeah, they have mahiawa as well. So, yeah.
What's that?
Mahiawa, it's the fish paste.
Oh, yeah. Yes.
There's something, I don't know what's the name of it. Does it have a specific name in English? Mahiawa. What type of fish is it?
The same.
Fish paste. Yeah.
Fish juice. What type of fish is it?
Anchovies,
Ah.
Yeah, okay.
It was very good.
Yes,
He really liked it.
Yeah.
So Yeah, I took him to we went to the first coffee shop in Kuwait. Do you know where is it? How old is it? It's 1780. 1780. It's Abu Nashi. Abu Nashi. It's in the Mubarakiya. Just for men. Just for men. Okay? Okay? No, please, leave some places for us.
Aye, aye, aye.
All right, thank you, Dr.
Thank you. Oh,
This is from the department.
Thank you.
Just want to take pictures. Thank you.
thank you very much. It's been a pleasure.